This is Sir Alex Vasco and welcome to our lesson in General Chemistry 1. Today we are going to start a new discussion on Lesson 10, which is all about the electronic structure of atoms. I hope by now you are familiar what atoms are. It's basically the building blocks of matter. It composes of subparticles or atomic subparticles like electrons, protons, and neutrons. And how is it related to chemistry? Well, a lot of the elements that we have, including hydrogen, helium, lithium, sodium, are all actually atoms. The only difference they have is the number of protons in them. For example, helium and hydrogen. The only difference between the two is the number of protons and electron. Hydrogens are atoms with one proton and one electron, while helium are atoms with two electrons and two protons. The main thing that differences from one element to another element is actually the number of protons. By increasing the number of protons, which is found in the nucleus of an atom, you are actually changing element. As again, let's take for example helium and hydrogen. Hydrogen has one proton, but when we add one more proton, what happens is it becomes helium. And if we take the helium core and added another proton, it means we now have three protons. And if we want to make this atom neutral, it means it has three electrons surrounding it. That atom now is actually lithium. So that is the difference among the elements that we have, and I hope you are familiar with that now. Having said that, what we are going to learn today is actually more about the structure of the atoms. More specifically, we are going to talk about the electrons, that is on our atoms. We are familiar with electrons in that they are not found in the nucleus, but they are surrounding your atoms. More specifically, they're surrounding the nucleus of your atoms. And previously, we've learned a design called the Bohr's model. It's a representation, albeit now it is we are not usually use it today, but for all intents and purposes, to make things simple, we usually use Bohr model to depict what an atom look like. But today we are going to learn more about the electrons and what how the electron behave around its nucleus, or how the electron in an atom actually behaves. So that is the bulk of our lesson today, which means at the end of today's lesson, what I want everyone to be able to do is use what we call the quantum numbers to describe the electron of an atom. Since our discussion revolves mostly about electron, there are certain numbers called quantum numbers that we use to actually describe these electrons. So at the end of the lesson, what I want everyone be able to do is to be able to understand what these quantum numbers are and what they do, how and what they describe about an electron. Next is to determine the magnetic property of the atom based in the electronic configuration. Later, we'll also learn how to identify the electronic configuration, and from identifying this, we can actually identify the magnetic property of an element or an atom that we have. And lastly, be able to draw the orbital diagram to represent the electronic configuration of an atom. Later, you will also know what an orbital diagram is. So these are the main three goals that we have today. This lesson can be really confusing. So while listening to this lesson, if there's anything that is confusing, please do not get discouraged. Just take time and practice and understand what is happening. It may take you 2 or 3 times watching this video, or you can also use outward resources in teaching you these. That is okay, because I understand that these things can actually be really confusing, but just keep striving and eventually you will get it. So let's begin our discussion by understanding what is quantum mechanics. Like I've mentioned before, initially when we describe an electron, or more specifically an atom, we usually use the Bohr's model. When we talk about Bohr's model, we usually have this type of situation going on here. So we usually have our electrons or our protons and our neutrons in the nucleus, and we usually draw a concentric circle a circle that is increasing in radius and enclosing the previous circle around it, and we usually add the electrons around this circle. That is actually the Bohr's model. Now we are not using these Bohr models anymore because it is actually inaccurate on how to actually describe the behavior of the electron and how to describe the structure of an atom. This structure right here is actually oxygen. It has 8 electrons. As you can see the electrons right outside its nucleus. You have 8 of them, and usually we have our first shell that can house 2 electrons, and then the next shell, and then the next shells that will go on will always have 8 electrons. That's how we have been drawing Bohr's model so far, and this tells us that our oxygen has 8 electrons, it has 8 protons, and actually has 8 neutrons in its nucleus. And all of this came about because we've used the classical mechanics in understanding how the electrons behave. When we talk about classical mechanics, it is a type of understanding how objects move in relation to our understanding with Newton's law of motion. I hope you are familiar with Newton's law of motion. This is our understanding on motion on a macroscopic level, on a normal level. So for example, when I move from point A to point B, how fast did I move? How far did I move? All of those encompasses Newton's law. But the issue with the classical mechanics and the Newton's law is that it only can describe the movement of our on a macroscopic level, meaning on a normal sizes like us, or the world where we move. The issue then comes is because these atoms are actually very, very small. They're very minute, which means because of their sizes, which is for all intents and purposes is not a macroscopic level, they're in a very small microscopic level. The classical mechanics basically disintegrates. It does not apply to the behavior of most of our atoms, or specifically the behavior of the electron. So there's another Bohr's model. This is thin right here. As you can see, when we draw Bohr's model, we're basically increasing the sizes of the electron, and each of the electron usually can encompasses more and more number of electrons. But besides the point, we know that this is actually not what the elements or what the electrons actually look like, because electrons does not have a set of place wherein they are. No, they are not only going in circle around the same place. In reality, electrons are actually much more difficult to identify where they are around the nucleus. And since we cannot use the classical mechanics to identify the position of the electrons, and the Bohr's model is actually a very poor representation of what an electron looks like, there's a need of another way in order for us to identify, or in order for us to visualize the behavior of the electron around the nucleus. And what we use is what we call the quantum mechanics. Because electrons, they're very, very small, and more importantly, they have what we call a particle wave-like or particle wave property, which means electrons can actually behave like a particle. You can think of it as like the simple ball that you have. If you throw a ball, it will go to one place from point A to point B. But also, electrons behave like waves, wherein they oscillate, they go up and down. For example, if you have your tennis ball and then you place it in an ocean, you know that your ball will not stay in one place. It will go up and down, and it will go in random places based on the wave of the ocean. And that is actually the behavior of the electron. It has both the particle property and has a wave property. In order for us to encapsulate this dualistic property of electron, what we have to use is not classical mechanics, because classical mechanics cannot handle this type of behavior of the electron. So what we use is called the quantum mechanics. So quantum mechanics is used to describe the behavior of an atom. More specifically, it is used for us to identify the predict the probable position of an electron. And we do this via the Schrodinger's model or the wave mechanics. What do we mean by that? So instead of taking the electron and just placing them around a circle like this, like what Bohr's model, or like what we do in Bohr's model, for the electron in quantum mechanics, what we do is we actually just have this bunch of area. This red dots that you can see right here is not the electron itself. It's the places wherein the electron can be found. And as you can see, if you take the electron and then trace the places where the electron can be found over a period of time, you would notice a pattern. And as you can see here, the pattern is around a circle surrounding the nucleus, right? So which means that the electron, as you can see the moving electron, that red dot moving around, this electron can be found anywhere around this red dot. And as you can see, as it moves around, it creates a probability, which means I can find my electron around this area of concentrated dots more. So much of the time the electron can be found around this area. So that's what quantum mechanics is. It's telling us the probability, or how much or how probable the electron is can be found at a certain location around the nucleus. Where in this scenario right here is in our example, it doesn't matter what this atom is, but the electron of this atom can be found around this certain area. It can be at this point right here, it can be at this point right here, or it can even be at this point right here. And that's what quantum mechanics is, at least in its the most basic form. It gives us the probability of finding of where to find the electron. And from the continuous studied, we actually were able to identify various orbitals. When we talk about orbitals, there can be various shapes or areas where we can find the electrons, which in turns we have something like this. So the area we're in, there's like whiter, as you can see here, there's a higher probability that you will find your electrons there. And the more darker the area is, the less likely that you will find the electron there. So as you can see right here, so take this for example, so those white areas right there, those are the probability that you will find the electron most of the time. And then the area we're in, it's a little more darker, a little more orange and even purple. That's an area we're in, it's less likely that you will find the electron. And the darker you go, for example right here, it's less likely, almost zero, that you will find the electron there. So because of our understanding that this is just probability, we were able to create these shapes called the orbitals. So we find that the structure of an atom, or the behavior at least of the electron, gives us not just a circle but various interesting shape like this. Again, this shape right here is not the shape of the electron, but this shape right here is where you will find the electron most of the time. It's just probability. Okay, so I hope that is clear. So understanding that, we can actually now use what we call quantum numbers in order for us to describe the various behavior of an electron. But before we can do that, let's go in deeper on how to identify this probability. How do we measure this probability? This is where we go and study what we call the main energy levels, sublevels, and orbitals. Because of the quantum mechanics and because of Schrödinger, we were able to create an equation which tells us the probability of finding where the probability of where we can find the electron, and also the arrangement of that probability. So the first thing that we have to identify is what we call So the thing that we have to understand are what we call first the main level, or the arrangement can be identified via three important things. First is the main energy level, the second is called the sublevel, and the third is what we call the orbitals. Main level basically refers to the shell in which the electron is located relative to the atom's nucleus, which means it is basically the distance where the electron can be found relative to the nucleus, meaning we usually denote it with a positive number integer. What do we mean by that is we usually use the number 1, 2, 3, etc. And then the higher the number, the farther the electron is from the nucleus. That's what basically this is. So main energy level refers to the shell in which you will find the electron, and then the higher the number of the main energy level, it means the higher the energy of that electron, and it is farther from the nucleus, which tells us, for example, if this is our nucleus of our atom, if you have an electron right here versus an electron at this point, this electron right here has lower energy level compared to the electron here. So the main energy level, this could be a main energy level of 1, and this could be a main energy of level 2. So again, the closer the electron is to the nucleus, the lower the energy level. Okay. The next thing is that within these energy levels, there's what we call sublevels. And sublevels depict the shape of the region. If energy level is the level that you will find the electron relative to an area, relative to the nucleus, or the distance relative to the nucleus, then the sublevel basically tells you what the shape of that area is. Okay. And these sublevels, we usually use letters to denote sublevels. This is what we call, or we usually use S, P, D, F, and then these are the most common ones, and then the next ones are usually we follow the alphabet: S, P, D, F, F, G, H, I, etc. So S levels or S sublevels usually tells you that the shape of the main energy level or the area where the electron is found is spherical, while P has kind of like it tells you that you have about like a 2 poles or two lobes. D had, it means you have about 4 lobes. F has 7 lobes. So we'll show that later on, but just remember, main energy level tells you where the electron is relative at the distance to the nucleus, while sublevels tells you the shape of the area where you will find the electron. So for example, let's have this table right here. So we have main energy level. So the first main energy level means this is much closer to the electron. You will usually find a sublevel S. So you will have your S right here. So this area right here, and in the middle right there is the nucleus. I just want you guys to think of that. So in the middle here is your nucleus. So the electron can be found anywhere around this sphere right here at the S level. And then interestingly, one thing that I want you guys to remember, these levels is actually determined by the main energy level. If you have one or main energy level of 1, it means you only have one sub level. If you have a main energy 2, it means you have 2 sub levels, which means for main energy level 2 or the electrons found at the main energy level 2, you usually have a sub levels of S and P. And also, if you have an electron that is found at the third level or the third main energy level, it means you would have about 3 sublevels, which is the sublevel S, sublevel P, and sublevel D, which means if I'm going to draw my main energy level at S sublevel, or we usually use this as shells and then subshells. So if you hear me talking about shell, I'm usually talking about the main energy level. If you hear me talking about subshells, I'm talking about the sublevels. So as for S sublevels, it is much more a little more bigger than our 1s. The reason for that, remember, our electron is found, or as our main energy level increases, the area usually gets bigger. Or what that means is that the electron is found farther and farther in the nucleus. So it means the electron is much farther than our nucleus. So by the third level, it is much more bigger. So you will find your you will find your electron much more farther than they are from the nucleus. So this is your 1s, 2s, and your 3s. And then, like I've said, the main energy level also tells you how many sublevels there are. So there's a second sublevel for main energy 2 level, or main energy level 2, which is the sublevel P. As for P, it usually has two lobes, and the two lobes is usually drawn something like this. So the electron is found around this area of your two lobes. As for, so this is your 2p, and then for your 3p, you would have something like this. So a lot more bigger. Remember, the electrons are much more farther. And since this is main energy level, you would have about a level of the sublevel D. As for D, you will have 4 lobes. So it will look something like this. So the electron is found along this shape right here. So this shape right here is telling you where the electrons can mostly be found. Okay, so that's what the sublevels are. So later on, we will use this more to identify not only what the shape of our atom is, but also to identify where we can find our electron. So those are the main thing if we want to find the area or the region of our electrons, or the region where our electron is situated. Orbitals, on the other hand, takes not only into consideration the shape of the sublevel, but also the orientation of that sublevel in space. What do we mean by that is, for example, if for our sublevel, we only have one what we call an orbital, because for most and foremost, the shape of sublevel is a sphere. And a sphere, no matter where you rotate it, the x direction and the z direction and the y direction will always be the same. So there's only one orbital at s level. But for p sublevel, there are about 3 orbitals. Again, orbitals is basically the orientation of our shape in space. So if we take the original drawing that I had earlier where you have your two lobes, remember this is our P, but as you can see, this is going in the z direction. But I can actually rotate this and make it so that it is along the y direction. As you can see now, this P sublevel is directed not at z but along the y. And then I can also take this and rotate it in such a way that it is along the x direction. So what tells you is for p sublevels, there are 3 orbitals, meaning there are 3 ways to orient this shape. And as you go deeper, what you would notice is that it gets more complex. For D level, remember for D, you can actually have you have 4 lobes, right? So this lobe right here, so you have your along the z direction, and as you can see, it looks like a circle because no matter where you rotate it, it's just along the z direction. And then I can twist it so that it is along the x direction, along the y direction, etc. So first you can see here, this is along the y direction, and then here is, where's the x direction? But no matter what Yeah, that's why it can get a little confusing. But just remember, for the sublevel, you have 5 orbitals, meaning there's 5 ways to orient this shape. And by the time you have at F, wherein you actually have 7 lobes, you have 7 lobes for F, and the shape is really confusing and it's really complex. There are 7 ways to orient that shape, which tells you, as you can see here, you're actually just adding 2. So as you increase your sublevels, you are actually increasing the number of orbitals by 2. So at least I hope you guys remember that, because that's easier to, or that's really easy to remember. So why are these orbitals important? Well, the reason for that is because each orbitals can hold up to 2 electrons. An electron that is going what we call a spin up and a spin down. Because if you have an electron right here, this electron can rotate clockwise, right? And this same electron can rotate counterclockwise. So what happens then is that we have to have a different designation as well of the direction of the rotation of this electron. For electrons that are rotating, when I said rotating, they're not rotating around an axis. They are rotating on their own. So you can imagine it na ikaw, nakatayo ka, tapos iikot ka. For example, ito ikaw, and then along your axis, you are spinning. As opposed to there is a chair, halimbawa yung journey or travel to Jerusalem or whatever, and then you are running around the chair. This is not what I'm talking about. This is the type of spin that I'm talking about. So think of yourself as an electron and then you spin. Umikot ka, yung parang tipong you can nahihilo ka, yeah? So this if you spin clockwise, that's a 1 spin, and this is spin we usually call what we call a spin up. And then sometimes you can stop and then you can spin in the counterclockwise direction, and if you think of yourself as an electron, that spin is called a spin down. So why is this necessary? Well, each orbital in each of the sublevel can hold up to 2 electrons, which tells you that for S sublevel, which only has 1 electron because it has a shape of sphere, it can only hold up to 2 electrons. While for P sublevels can hold up to a number of 6 electrons because it has 3 orbitals. As for D with 5 orbitals, it can hold up to 4 electrons. So the number of electrons for each sublevel increases by 4. So that's another thing that I want you guys to remember. For each sublevel, the number of orbitals increases by 2. For each sublevel, the number of electrons increases by 4. You start with 2 and then you keep increasing 4. Okay, so the reason for that is let's talk about S. We usually draw like a box or a line to denote the orbital. So for S level, let's say 1s or even 2s, right? A 1s main energy level of 1 at a sublevel S can hold up to 2 electrons. And when you are writing the electron that can be held in the orbital, you usually have to start with the upward sign, and then you would go downward. So which means this sublevel right here, its orbital, because there's only 1 orbital, is fulfilled. So this sublevel here has filled its electron share, and we can usually write 1s2. So the number there is usually the number of electron this sublevel has, and this is your main energy level. So these electrons are very close to your electrons, and its shape is in the sphere, so meaning you will find your electrons right here around any part of this sphere right here. And this electron, one electron is spinning up, and one of the electron is spinning down. But if you have p, let's say if you have, for example, p levels, you will usually have about 3 boxes because you would have 3 orbitals. And when you are writing or filling these orbitals with electron, according to one of the rules, you have to fill each you will have to fill all of the orbitals first before pairing. So for example, we have an element with 5 electrons. In order for you to fill this up, what you need to do is you need to write fill starting with the spin up, and once all the orbitals is fulfilled, then that's when you will write all your spinning down electron. So this p is p5, something like that, which means this sublevel has 5 electrons in its orbital. Okay, so which means you have something, yeah, you have something along the line. So 1 electron right here and another electron right there, and then you have another 1 electron right here, another electron right there, and then 1 electron that is going up. So that's what basically what this is. Each orbital, each of the shape can hold 2 electrons. Okay, so I hope it's making clear. Like I said, it can get really confusing, so please, if it's confusing you, go back and study, or I encourage you search other resources as well. Okay, so those are the main difference between you have your main energy level, you have your sublevel, and then now we just discuss orbitals and how many electrons can be stored in one orbital. Now let's talk about quantum numbers. Quantum numbers is what we use to again describe the behavior and of the electron. The first quantum number that we have is called the principal quantum number and is usually denoted by n. Principal quantum number basically corresponds to the main energy level, which, like we've discussed, the main energy level tells you how far the electron is from the nucleus. The higher the number is, the farther the electron is from the nucleus. So 1, it has the lowest energy level, which means it is closest to the nucleus. 2 is a little farther from the nucleus to compared to 1, and then for 3 it is way more farther compared to 3 or compared to 2 and 1. So the principal quantum number is just telling you the main energy level of that electron. Next, you have what we call the azimuthal, or this is actually the angular momentum quantum number. Angular momentum quantum number corresponds to the sublevel where electron belongs. Remember, sublevel tells you where the electron is, right? And remember, for sublevel, it could either be an S, P, D, F, G, H, I, blah blah blah. And the value for the azimuthal, or which we usually write letter L, since this is sublevel, it can vary from 0 to n-1. So if you have a sublevel of or main energy level of 1, your L will be 0 because you have your n is n-1. If you have, for example, an n main energy of principal quantum number of 3, which means you are at the third main energy level 3, your L can either be 0, 1, and 2. Okay, which means these sublevels can either be 0, 1, or 2. And for azimuthal, 0 is S, 1 is P, 2 is D, which tells you that for an electron with a main energy, or for an atom with a main energy level of 3, it can have a sublevel of S, P, and D. Okay, so that's what basically the quantum or the angular quantum momentum number, or the angular momentum quantum number is. So it starts from 0 and then it stops at n minus 1. And again, 0 is S, 1 is P, 2 is T, and 3 is equals to F. As for 3, for an electron that is already at the F sublevel, it means that your principal quantum number, or your main energy level, is already at n is to 4, which means you would have your S, P, D, and F on that atom. Okay, so I hope I'm explaining this enough, but that's how you identify your azimuth L, or your L. The next quantum number that we have is called the magnetic quantum number. Magnetic quantum number, or M sub L, identifies the specific orbital in the sublevel where the electron can be found. Remember, each of our sublevel has a different number of orbitals. If you remember, S orbital has, or S sublevel has 1 orbital, P has 2, or no, 3, D has 5, and F has 7 orbitals. And this is basically for magnetic quantum number. M sub L identifies the specific orbital. So since you have more than 1 orbital, especially for PDF, it tells you specifically what orbital sublevel where the electron can be found. And we usually have the range of M sub L is equals to negative L to positive L. So for our M sub L, for if you have a P is equals to 3, our M sub L can be negative 3, 2, 1, 2, 3. Right. Yeah. No. Sorry. This should be for P you have 3 orbitals, and the L for P is equals to L level is equals to 1. So for M1, it means you would have about negative 1, 0, and 1. So this numbers right here tells you the different orbitals that you will find in P level. I hope I'm explaining this enough, but yeah. So for L is equals to 0, so if you have your L is equals to 0, it means your sublevel is at S. For L is equals to 1, you would have your P. And this L also is the one that you will have for your M sub L, which again for M sub L tells you the specific orbital. So for P, we know for sublevel P, it has a azimuthal, or angular momentum quantum number of 1. So our M sub L can either be negative 1, 0, and 1. 3, which corresponds to the 3 orbitals that we can find in P sub level. So if you notice, these numbers are basically the ones we discussed earlier. Your principal quantum number is your main energy level. Your azimuthal is your sublevel, while the quantum or the magnetic quantum number is the orbital, the specific orbital where each of the orbital can have at least 2 electrons in them. And the last quantum number what we have is called the spin quantum number, or S, or M sub S. And this is determined depending on the electrons that we have. So the spin of the electrons. So for the electrons that is clockwise, we usually denote a positive 1/2, and for the electrons that is going counterclockwise, it has an S level of either negative 1/2. So these are the 4 quantum numbers that we identify, or that we use to describe the behavior of the electron. Now, where do we use this? Where we use this in what we call the election configuration. Election configuration is the logical numerical representation of the predicted locations of the electrons in an atom. This is what we use in order for us to describe the behavior of the electron that we can find in our element. Later, you would see on how we use this, but that's the use of election configuration. And then we have what we call the orbital diagram, which is what we use to illustrate the distribution of the electrons in each of the orbital. The orbital diagram is basically the one that I showed you, wherein you would have situation like this. For electrons that is spinning up or clockwise, we use the arrow pointing up. For electrons going or spinning counterclockwise, we use the arrow pointing down. And there are some principles that we have to follow when we are drawing or illustrating the orbital diagram. The first principle is called the Aufbau principle, or the Aufbau principle. It tells us that the electrons must occupy the lowest subshell first. So meaning our electrons must occupy the S level first before occupying the P, the T, and the F, etc. And later I will show you the mnemonic or how to remember the Aufbau principle. Next, we have the Hund's rule. Hund's rule is that the generate orbitals must be filled first by single electron before pairing pair. So remember, for Hund's rule, for P, we know that we have 3 orbitals, right? And these orbitals of M sub L can either be -1, 0, and 1, which means we can draw it something like this. So according to Hund's rule, when we are drawing our orbital diagram, we usually have to fill our orbitals first, and the generate orbitals are the orbitals at the same level. So you have your different orbitals and they are all at the same sublevel. And after filling all of that, that's when you can pair the electrons. So according to Hund's rule, make sure you fill all the orbitals first before giving them a pair. And lastly, Pauli exclusion principle, it tells us that only 2 electrons can be stored inside one orbital. So it can, and also the electrons that can be placed inside the orbital, it should only be either going up or going down. You cannot place an electron that is both going up or both going down. This too is a no-no. The electron should go up and the electron should go down. So applying this principle, each electron actually should have very unique quantum numbers. Okay, so even with you have an element that is falling at the same sublevel, the spin quantum number, whether it is positive 1/2 or negative 1/2, will change because the orbital can only have 2 electrons and they're both spinning in the different direction. So every electron has very different quantum numbers. So this is where we use the Aufbau principle. So the Aufbau principle. According to Aufbau principle, so the electrons must occupy the lowest subshells first, meaning we have to occupy the lowest subshell first. So when we are writing our election configuration, we start with 1s, and then after that we go to 2s. So we start with 1s and then 2s, and after that we go to 2p, and after 2p we move to 3s, 3p. And then what is interesting at this point right here, what you would think is you would have to fill 3D first, but that is not what's going to happen. So after 3p, the thing that you have to fill out first is actually 4s before filling 3D. Okay, so this is the direction. Something that I want you can use this to remember how to fill your election configuration. You start with 1s and then 2s, 2p, 3s, 3p, 4s, and then 3d, 4p, 5s, 4d, 5p, etc., etc. This is the direction that we use in filling up configuration. And then next, diamagnetism versus paramagnetism. Diamagnetism basically is the property of an atom with pair electrons. An atom that has all its electrons pair is called a diamagnetism, which means it does not get attracted to a magnetic source. So if I have an atom right here and I have a magnet right here, very usually it's a huge magnet, right? This electron will not get attracted to that magnet. It's because all the electrons are paired. Because when an atom has an unpaired electron, it becomes paramagnetism. What happens is that because of that unpaired electron, that atom, so this is your atom and you have your magnet right here, what happens is that it actually gets attracted to that atom. So there's a flipping on the, which we call the flipping of the electron. We're not gonna go in that or the flipping of the electrons, but just remember this: if all the electrons on each of the orbital are paired, then that atom is diamagnetism or diamagnetic. If the atom has an unpaired electron, then it is a paramagnetic, or it is being attracted to the electron. So next, how do we apply this in a sample problem? So these are the steps that you can follow in answering sample problems in regards to quantum numbers and electron configuration. First is write the electron configuration. To write the electron configuration, we use the Aufbau principle, or basically this mnemonic right here. You follow this and write the number of electrons in each of the orbitals or in each of the sublevel. Next is accomplish the orbital diagram. What that means is we have to write in your you basically have to draw your your spin up and spin down electrons on this could be a square or even just a line. And then lastly you determine the quantum numbers based on the last electron in the orbital diagram. So let's see and try this sample problem. Determine the quantum number for a neutrally charged magnesium atom. Is magnesium diamagnetic or paramagnetic? So if you look at the periodic table, magnesium actually has 12 electrons, right? So let's write that. So magnesium actually has 12 electrons. So what we are going to do is we are going to write the electron configuration. And you can do this separate with your orbital, but what I'm going to do is I'm gonna mix it with the orbital already. Okay, so magnesium. So the first one that we have to do is we have 1s. So at 1s, we know at 1s it has what? How many electrons we how many orbitals that we have? This line here represents your orbital. We know that 1s has one orbital, and each of the orbital can have 2 electrons. And according to the Pauli exclusion principle and the Hund's rule, so we have first, according to Hund's rule, we have to first fill this lowest shell or this lower main energy level. So I'm gonna write the electron going up and then write the electron going down. So that fulfills my 1s. The next one is 2s. So I already have 2 electrons right here, so it means I only have 10 electrons left. And again, s has 1 orbital, right? So for 2s, so again I have to fill this electron or this orbital first. So I'm gonna write an electron going up and an electron going down. Alright, okay. Next here, So I have already 4 electrons. I'm not done yet. I need 12 electrons. The next main energy level and sublevel is 2p. Next is 2p. So how many orbitals does a p have? Remember, sublevel p has 3 orbitals. And according to Hund's rule and the Pauli exclusion principle, or Hund's rule more specifically, I have to first fill in these orbitals using the sign up. So how many electrons do I have? So these arrows represent your electrons. Okay, so I have 1, 2, 3, 4, 5, 6, 7. So I have 7 electrons. 8, 9, 10. So I have 10 electrons so far, and I'm at 2p. So after 2p, the next is 3s. And s has 1 orbital, so meaning I only have 1 line right there. So how many electrons do I have left? I have only 2 electrons left, and coincidentally for 3s, so I need to write an electron going up and then the electron going down. So this is already my orbital diagram right here. And it's not yet the electron configuration, but it's already you already have a clue on how to write the electron configuration. So the electron configuration of magnesium is actually 1s, and then you're going to write 2 because you have 2 electrons on that s configuration or that s orbital. And then you have your 2s2, 2p6, 6 because you have 2, 4, 6 electrons, and then 3s2. So the electron configuration of your magnesium is 1s2, 2s2, 2p6, 3s2. Okay, now let's identify the quantum numbers. Okay, so the quantum number n, based on my last selection, the last selection is at main level number 3. Remember, my principal quantum number is basically the main energy level. So the main energy level is 3. And then my L, which tells me the shape of my, or basically the sub-level. Since it's in the S direction, then my L should be 0. Remember, for our for the angular momentum quantum number, L is equals to 0 if it is S, L is equals to 1 if it is P, L is equals to 2 if it is D, etc. It is F. Since we are at S level, then my L is 0, which tells me my M sub L should be 0. Because M sub L, how do you identify that? That's negative L to positive L. But we only have 0. So our M sub L, our L is 0. So that's 0. There's no negative 0. There's no positive 0. So we only have 0. So our quantum numbers, M sub L is S, or is 0. And lastly, our M sub S, or our spin. The last electron for our spin is what? Going down, right? Since our last electron is going down, so going down is what? It is counterclockwise. So our S is negative 1/2. So these are all your quantum numbers. And lastly, let's ask, or let's identify, is this diamagnetic or paramagnetic? Well, remember, diamagnetic, all electrons are paired. Paramagnetic has unpaired electron. And since all our electrons are paired, this tells me that magnesium is diamagnetic. So those are the answers for sample problem number 1. And lastly, let's try and go sample problem number 2. What is the unknown element if it has a quantum number? So let's write our given. They gave us a quantum number of 2, or principal quantum number 2, which means we have a main energy level of 2, and then we have our sublevel, our angular momentum quantum number 1, which already tells you that this should be at the p sub level. And then you have your m sub l of 1, so which means the last electron that we have is, since this is m sub l, we have an l is equals to 1, so it should be negative 0, negative 1, 0, or 1, which means our electrons are found at number 1. And then our s is positive 1/2, which means this is our last electron is clockwise. Okay, so let's identify this element. So by first, let's find the electron configuration. Okay, and our orbital diagram. So our first clue is our main level is n, so it means we are past our 1s. Remember, our 1s main energy level of 1 has 1 orbital, so it will have 1, 2. And our next is we have 2s. So now our principal number is checked. We are at main energy level 2, and so let's write this. But our L is 1, right? L for S is 0, which means our sublevel should be at P, which means we are not at 2s, but we should be at 2p, which has 3 orbitals. So our L is now checked. We have our main energy level, or principal quantum number 2, our angular momentum quantum number 1, which means it should be at P, and then next our last electron should be at 1. It means our last electron should be here. And we note that the spin of our last electron should be clockwise, which means it should go up, right? So let's fulfill this. Let's go 1, 2, and then we are going to write, according to Hans' rule, we should first fulfill all our orbitals, and we are done because we are at 1. Our ML is at positive 1, which is right here. And our spin quantum number for our spin quantum number is at positive 1/2, which means our electron should be going up. So this is our orbital diagram, and our electron configuration is 1s2, 2s2, 2p3, right? And this means we have an atom with 7 electrons, 2p3, and this atom is actually nitrogen. So this element is nitrogen. So how do we identify that? Well, if you look at here, so this is our S block. So this is our 1s1, 1s2, and then this is our n equals to 2. So this is our 2s3, 2s, or 2s1, 2s2, and then we are going to p block. So this is our 2p1, 2p2, 2p3, and that is our nitrogen right there. So you can actually also use your periodic table to identify the electron configuration. So let's try chlorine. So what is the electron configuration of chlorine? So we know that this should be at N is equals to 3, and our chlorine should be at P block, right? So if you're going to write this, so we have our 1s2, and then we fulfill our 2s2, and then we fulfill all of this right here, which is our 2p6, because this is 2p4, 2p5, 2p6, and then we have our n level at 3. So you have your 3, and this is your 3s1, 3s2. So that is 3s2, that is fulfilled right there. And then you have your 3p1, 3p2, 3p3, 3p4, 3p5. So this would be our 3p5. This is the electron configuration for chlorine. And there's actually a shortcut here. So you can have a gray ground state right here. So you can choose like an element that's stopped right here and use that as your ground state, which tells you that at 2p6, this 2p6 right here is neon. So you have your neon, and then just continue on. So you have your 3s2 and 3p5. So you can write it this way, or you can write it this way as well, because this right here is equals to that one. So I hope it's clear how to do this. If you guys have any question, do not hesitate to message shoot me a message, and I thank you so much, guys, and have a great day.